Welcome everyone. In this video I will prove that resistance is proportional with length and it is inversely proportional with cross-sectional area. So to make my proof, which I said is hopefully the goal of this video is to prove that resistance is proportional with length and it is inversely proportional with cross-sectional area. So it is proportional with the reciprocal of area. And this was supposed to be a 1, even though it doesn't really look like a 1. So how can we prove this? Well, to make our proof, let's say, and for the first case, let's say that we have a cylinder like this. And imagine this as a close-up look of a wire. You know, in circuit diagrams, we usually draw wires just like these lines. We only make them lines. We have a resistor like this, maybe a battery. That's not a battery. But anyway, you get the idea. So imagine that this is the close-up look of a wire. And every wire in reality has a resistance value, right? No wire is perfectly capable of conducting electricity. So every wire has some resistance. And if we have this wire, and you add another one to it, again cylindrical, this length, let's call it L, and let's call this one L as well. They have the same cross-sectional area A and the same resistance value R. Now, we know that there will be a voltage between this and this point, and there will be another voltage between this and this. So there are two electric potential drops, to say, and the current flows in this way, which we use I to represent it. I means the current, V means the voltage, and capital R means the resistance. So we can observe that I goes through each resistor, each cylinder that we have, and using Ohm's law, let me write it here, maybe Ohm's law, we know that the voltage is equal to the current times the resistance, which means I is equal to V over R. Using this idea, we can write for our case the same thing, V divided by R. Now, this is correct for each of the resistors, each of the cylinders. But if we want to look at the whole picture, if we want to look at the whole of it, then we can say that we still have the same current that is passing through individual resistors. And if you look at them as a system, still the same current passes through them. But now the voltage changed, right? We don't have just a 1 voltage drop, we have 2 drops. So we have 2 drops, we have 2V, and now we have a different resistance value, R equivalent, I will call it. And if you look at this equality, you can see that R equivalent is equal to 2R. Well, what does this mean? This means that since R corresponded to the resistance when we have length L, and R equivalent corresponds to the resistance when we have 2L, you see that when we doubled the length, the resistance value doubled as well. So this helps us to conclude that resistance is proportional with length. Now we did half of what we were hoping to do. This one is checked. And that wasn't a nice check, this one is checked. And now let's try to prove that resistance is inversely proportional with cross-sectional area. So I will draw a cylinder again. But this time, instead of drawing one next to it, I will draw one below it. Like this. These again have resistance value R, length L, cross-sectional area A. Now, if we look at this thing, and let's say that I is flowing like this. If you look at this, you know that only half of the current that we have will flow through individual resistors. So if we are only interested in this guy right here, we will say that using Ohm's law, I over 2 will be the current that flows through it, and there will be a voltage drop which will be divided by R. So this is what Ohm's law gives us. And if we were to look at the whole situation, if we were to consider the whole system, what would we see? Well, if we consider the whole of it, we will have I. This time the whole, the whole current will flow through our system. This will be equal, and this is the tricky part perhaps. This time we have the same voltage for our system and for our individual resistors, right? The voltage is the same. Not like the last case, because in the last case we were adding the voltages, which I hope makes sense to add. But for now, in this case, we don't need to add them, because for one resistor we start at this point and end at this point, and when we look at the overall picture we still start at that point and end at that point. So we are good. And we will divide this by our equivalent. Alright, so if we combine the two equations that we see using the first one, we see that I is equal to, if we multiply both sides by 2, 2V divided by R. So if we substitute it here, we will see that V divided by R equivalent is equal to 2V divided by R. You can simplify by V, so that you get R equivalent is equal to R divided by 2. Well, R was the resistance value when we had a cross-sectional area A, and R equivalent was the resistance value when we had a cross-sectional area of 2A. As you can see, when we doubled the area, the resistance halved. It got less. It got 2 times less. So we conclude that R is proportional with the inverse of cross-sectional area. Now, if we combine our last result, this one, with the result that we just got, we see that R is proportional with L divided by A. If you want to make this proportion, if you want to make this proportionality an equation, an equality, then you can say that R is equal to rho times L divided by A, where rho is our equality constant. And the equality constant also has a name. It is called resistivity. It is a thing that the metal itself decides on, right? If you use a different type of wire, then your resistivity, the value of the rho will change. And we prove that the resistance value, if you don't change the resistivity, if you don't change the material itself, if you double its length, the resistance doubles. If you double its cross-sectional area, then the resistance halves. And I hope this makes sense, right? If the electricity has a greater distance to go, well, then we expect there to be more resistance. And if it has more space to pass through, so in other words, a greater cross-sectional area, then we expect it to pass easier, so that the resistance should decrease. And that is the case, just like we proved. I hope that this video was helpful. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.